We start at 7:15. Okay. So I hope that you are okay with the quiz, right? It's only how many percent? Maybe 18%, so it's okay, right? Actually, I have already designed the final, so hopefully that would be as easy as this, all right? But this is the standard, huh? All right. I'll post the solutions tonight. Okay, so can the people in Zoom hear me? Cai Ting, can you say something? Can you type something so that the people in Zoom can hear me? Okay, good. Right, so now let me make this full screen. How do I make this full screen? Close here. Okay, this is better. Right. Oh, okay. So now we want to resume our discussion on Markov chains. We have to open the chat. Okay. Yeah. Okay. We would like to resume our discussion of Markov chains, and today we will talk about the stationary distribution and when we have a stationary distribution. Okay. What's the difference? Okay, yeah, that's what I want. Okay, so let's review Markov chains and let's review some important definitions. So a discrete time Markov chain, and we only talk about finite state. Okay, so I'm not going to repeat the fact that, okay, maybe I am. A discrete time, finite state, and homogeneous Markov chain is nothing but a sequence an infinite sequence of random variables that are called xn, okay, in which each xn belongs to S, and here S is a finite set, and it has the property that probability, and this is the Markov property if you wish, xn minus 1, xn minus 2, all the way down to x0 is equal to the probability of xn condition on xn minus 1, and this holds for all n bigger than 1. So the intuitive reasoning is just that this conditional distribution is equal to this, far away enough to take off the noise. This conditional distribution is equal to this because once we have information about the immediate past, we don't need any information about the rest. So that's what this is saying. All right, this is the definition of a finite state Markov chain. All right, so you have seen this before. States I and j in S, of course, communicate if I is accessible from j and j is accessible from I. So we denote this by this, and j is accessible from I. In which case we write that I communicates with j. All right. So I'm not going to talk about what is meant by this and this. This means basically that there is a walk of an arbitrary length from I to j. Okay. So a definition, a class, and I will surely ask you what is a class of states. A class C of states, let's say in S, is a non-empty subset of S of states S, such that for every I in the class and every other state J not equal to I, we have to do the following check. It satisfies J in C if and only if I communicates with J, and J not in C if and only if I does not communicate with J. Okay, so last time we saw many examples of this, so I will not belabor the point. But you need to know that you need to be able to identify the classes if I give you a Markov chain. So a recurrent state, and this is the family of states that we will be interested to work with, is a state I that is accessible from all states that are accessible from I. From all states that are accessible from I. So mathematically, what this means is that if J is accessible from I, then I is accessible from J. Okay, so if there is a state J such that I that there's a walk from I to J, then it must be true that there must also be a walk from J to I. So that is the meaning of recurrent. Okay, so that is the meaning of recurrent. Transient state is one that is not recurrent. So there are only two types of states. Now, this is true for finite state Markov chains. If you deal with countable state Markov chains, there could be many other classifications. Not recurrent. But these are the only two classes of states that will concern us, recurrent and transient. Okay. So we also talked about period. The period of a state I, is equal to the greatest common divisor of those n's such that PIIN is bigger than 0. So you should be able to tell me what is the period of a particular state by just evaluating this formula GCD. So we proved the following two theorems last time. Okay, for a finite state homogeneous Markov chain, Number one, either all states in a class are recurrent or all are transient. It's just to refresh your memory. And number two, given a particular class, all the states in the same class have the same period. Have the same period. So we can say that this class has period n. This class is a recurrent class, all right, because of this theorem, okay? All right, so this is all that we talked about last time, summarized into 6 minutes of discussion, okay? We proved all these, we defined and proved all these results. So today we're going to go beyond. So the motivation for today's lecture is actually, we want to study the long-term behavior of Markov chains. Suppose I throw you into a Markov chain, okay? After a very long time, how long will you spend in state 4? How long will you spend in state 6? Will you spend a lot of time in state 6, or will you, on average, never spend any more time in a particular state? So we'll see this in a short moment, okay? So that's the motivation, because we are interested to understand the long-term behavior of Markov chains. So let's define an ergodic class. Okay, this will be of particular importance to us, is one that is recurrent and aperiodic. I forgot to review the notion of aperiodic. An aperiodic state is one with period 1, okay? So an aperiodic class is one in which all the states inside have period 1. All states have period 1, and hence aperiodic. So that's the notion of ergodic, okay? So we have the following result, okay, that we won't prove, okay, that we won't prove, but it is proved in, I think, problem 4.5 of the book, okay? For an M-state Markov chain, right? Pijm. I think this statement is not quite correct. I need to look at the book for a while. Sorry. I'm not 100% confident that I wrote down the correct thing. I think there may be an error in what I've written here. Sorry, yeah. I just want to make absolutely sure. Do we need ergodic here? I suspect so. Okay, so what I want to say is that after a long time, all the elements of the matrix will become positive. Okay. Oh, okay, moving on. For an M-state Markov chain, Pijm bigger than 0 for all ij in S, okay, and all m bigger than or equal to m minus 1 squared plus 1. Okay, so this means that after a long enough time, everything will be positive. Okay. The book, does it say so? Oh yeah, that's why I found it very, very funny. My notes was very funny for an ergodic M-state Markov chain. Otherwise, there's an issue, right? Yeah, that's right. That's right. Sorry. So an ergodic M-state Markov chain, then you have sufficient mixing throughout. All right. So after a long enough time, all the elements of the matrix will be positive. All right. No, so this will not be true for any Markov chain. For example, if I have the state transition matrix given by this, okay, so what does this represent? This represents a two-state Markov chain in which we just do this, okay? So it's very uninteresting. So no matter how much you exponentiate, you take the power of this matrix here, this is an identity matrix, the zeros will always be retained, okay? So similarly, if we have the Markov chain given by the following skew symmetric matrix here, then how does this look like? So basically we have a periodic class here of period 2, okay? So you'll notice that once we take powers of this, then p to the odd, let me do this properly, p to the k will be equal to 1, will be equal to identity. No, I mean this skew symmetric matrix. Okay, it will be equal to the identity matrix if k is even And if K is odd, then you will have the skew symmetric matrix here. Okay, so there are only two possibilities. So in this case here, what happens is that you will always see zeros. All right. It is not true that after a long enough time, everything will be positive. So these examples are precluded. These are not ergodic. All right. So I just want to remove all this to make the notes look nice. Okay, but you can think about this later on. You can revisit the video if you want. Okay, so I will not prove this. This is exercise 4.5 of the book, and if you are interested, I have put it as an optional problem, and I will produce the solution for you. Okay, this is a little bit too involved to be proved in class. Okay, and that's why you see that this is important, because after some time, this entire matrix is all positive. Now, for a Markov chain, you know that the matrix that you are dealing with is a non-negative matrix, a row stochastic matrix, but there could be a lot of zeros. And zeros cause problems, all right? Zeros preclude the movement from a particular state to another state. So that always causes problems. But if all of them are positive, then we can talk about steady state behavior, which is our motivation in the next part of the class, okay? So before I talk about this, I want to talk about a little bit on the matrix representation, okay? So again, we have the matrix, a stochastic matrix, a row stochastic matrix, a row stochastic matrix. This is P, i.e. all rows add to 1. All row sums are 1. All row sums are 1. I talked about this last time. So we have the following definition. This is the probability that xn equals to j condition on xn minus 1 equals to I. Okay. So that is the probability that I transition from I to j, and this holds true for all possible n bigger than 1. So that's just nothing but the probability of going from I to j. All right. So we're going to ask the question. Okay, this can also be written as Pij. Let's keep it simple. Pij2. What does this mean? That is nothing but the probability that x2 is equal to j condition on x1 is x0 is equal to I. Notice that the difference here is 2, reflected by this. So at time 0, I'm at I, at time 2, I'm at j. How do I express this in terms of the state transition matrix? Okay, so now the natural thing to do is to condition on x1. So we have x2 equals to j, comma, x1 equals to k, condition on x0 equals to I. Here we are just making use of splitting of probability. So this is sum over k, probability of x2 equals to j, condition on x1 equals to k, x0 equals to I, probability of x1 equals to k, condition x0 equals to I. So this base rule. Now, here we are going to make use of the Markov property in which we are going to remove this term here. This holds true by Markovity, by the fact that we are dealing with a Markov chain. So this is k, the probability of x1 equals to k, condition on x0 equals to I. Okay, we did this calculation last time already. But by the definition of matrix multiplication, this is nothing but, no, not matrix multiplication. By the definition of the state transition matrix, this is nothing but Pik. Maybe I should write this as Pkj Pik. All right. So this part here is basically this part here, and this part here. I meant to use a different color. This part here is nothing but this part here, right? So I'm not cheating here. Hopefully you see that this is the case. But this is nothing but if I take the matrix P squared, this is the ijth entry. Okay, so the conclusion here, the moral of the story is that the two-step transition probabilities are given by the elements, of the product matrix P squared equals to P times P. Okay, so this is very convenient, and it actually justifies this notation here. Okay, we put a 2 here to signify that we are actually moving 2 steps. We are actually considering 2 steps from I to J. Okay, but actually this notation here also hints at we are doing a second order power of the original state transition matrix. Okay, so this notation here is consistent with power of the matrix ijth element. Okay, does everyone follow this derivation? Does everyone follow this definition? Any questions? Any questions? So here we are basically just using the fact that here, this is the definition of Pij2, but this 2 is not square. All right, this 2 signifies that the difference between these 2 indices is 2. Here we condition on x1 taking on a particular state k. And then here we make use of the Markov property to drop this red part here. But these 2 are exactly Pik, Pkj. And this is the definition of matrix multiplication of 2 matrices. Okay, so I'm not going to, of course not going to do the m power case. So Pn represents the Pnij or equals to Pijn is the ij entry of Pn. All right, so let's say this. Pijn is the ij entry of Pn and represents probability of xn equals to j condition on the fact that x0 equals to I. This is the n-step transition probability. And this is the n power of the matrix P. Okay? So this notation is consistent. Of course, we also have Pm plus n is equal to Pm, Pn. All right, all these matrices are the same. All right, Pij m plus n is equal to sum over all possible values of k, Pikm, and Pkjn. All right, so here this is a special case, this is a generalized case of what we did just now when m and n are equal to 1, 1, 1, 1 here. So here I'm just doing, I'm just basically considering an n-step transition from, an m-step transition from I to k, and then an n-step transition from k to j to get the m plus n step transition from I to j. All right, so this is a method of matrix multiplication. Okay, so our goal, as I mentioned just now, we would like to understand the long-term behavior of the Markov chain. So in particular, this as n tends to infinity. Okay, so in particular, we would like to ask a certain question. Okay, we have a certain Markov chain, and we can start at any state. All right, there's a certain probability we start at state 1, certain probability we start at state 6. Now, if after a very long time, you forgot where you started from, then that is an interesting situation. But consider this particular state transition matrix. Okay, this is a very strange Markov chain. Okay, I told you that at time 2, you were at 2. Then, all right, I told you that at time 2, you were at 2. I told you that, now I tell you a different story. At time 100, you were at time 2. At time 100, you were at time 2. You were at state 2, sorry. At time 100, I am at state 2. All right. Where was I at time n equals to 1? You can tell by working backwards. All right. So if at an even time you are at state 2, that means for all even times you are at state 2. So this guy is odd. right? So you must be at state 1 here. So you've never forgotten where you came from. You've never forgotten where you came from. Okay? So this is a very simple example to tell you that actually this guy here is not converging into a rank 1 matrix. All right? But I will explain what I mean by rank 1 matrix shortly. All right? So let's just write this down to be more precise. Note that if the memory of the starting state, let's say I, dies out as n tends to infinity, then the Pij n should become independent of I as n tends to infinity, and only dependent on j, or only dependent on where you ended up, not where you started from. So remember, our convention is that I is where you started from and j is where you end up. So if after a long time, this particular quantity here depends not on I, but only on j. All right? That means you've forgotten where you came from. Okay? In other words, we have the following situation sometimes. Okay? This guy here, this matrix here converges to P11 infinity all the way to P1m infinity, PM1 infinity, all the way to PMM infinity, converges to this particular matrix. And this looks like pi 1, pi 2, dot, 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 pi m, pi 1, pi 2, dot, 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 pi m. So this particular matrix here, okay, can differ in the columns, but it does not differ in the rows. The rows are all the same. The rows are all the same, okay? And in particular, this is a rank 1 matrix. Because all the rows are the same, right? That everything is linearly dependent on just one thing, right? So in this particular case, in this very special scenario, and we will see a demo that I hopefully we can make work, all right? That in this particular case, all right, we forgot where we came from because the long-term proportions of where we end up are given by this. This is what we call a steady state vector. Okay, so basically now Pijn as n tends to infinity does not depend on I anymore because all the rows are the same, right? All the rows are the same. They only differ in the columns. Okay, so does everyone understand this? This is the crux of what we are doing today. So this guy here, this is the probability that I go from I to j in n steps. As n becomes very large, if this does not depend on I anymore, then what happens here is that this matrix here converges to a rank 1 matrix here. Because it does not depend on I anymore. No matter which I choose, I see the same row vector pi. The same row vector pi. It clearly depends on where I end up. All right, where I end up. Okay, depends on which state I end up, which is the state j. Okay, the proportion of time here. But I forgot where I came from because this is a rank 1 matrix. They do not differ across rows. Okay, so suppose such a pi exists. All right, how do we find it? And we'll see conditions under which a finite state Markov chain has this particular behavior of converging to this rank 1 matrix. We'll see a particular examples and conditions. But suppose it does exist. How do we find it? To find pi, assuming it exists, then we refer back to the this is called the Chapman-Kolmogorov equation, n+1. So let's look at the Chapman-Kolmogorov equation, which is the probability that I move from I to j in n+1 steps. How is that related to the probability of traveling from I to k in n steps and moving from k to I in 1 step? Okay, so this is summing over all possible k in the state space. Okay, this is nothing but the usual type of equation. This, by the way, is called Chapman-Kolmogorov equation. Okay, so now what happens here? All right, if I let both sides tend to infinity, if I let n tend to infinity on both sides, then what do I get? Well, what you get here is pi j, because I already said that if we have this behavior here, that this matrix here converges to a rank 1 matrix, then this guy forgot where it came from. It forgot the I. So the only thing it remembered is where it ended up, which is pi j. Now, similarly, this would go towards pi k, right? This basically converges. Let me do this. This converges to this converges to this, right? Because I forgot where I came from, I only remember where I ended up, and this is pki, and this is sum over all possible states k. All right, so this equation now, if you look at it carefully, all right, can be written as pi equals to pi p. Now here pi, I will write pi as pi 1 dot 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 pi m, row vector. All the pi's are row vectors, okay? Row vector. So in conclusion, if it exists, okay, and this is called a steady state vector, I'll define it properly later on. If it exists, we look at this particular equation and we solve it in order to find the steady state vector, which I have not defined yet. Now, whenever we write a matrix vector multiplication, we have to make sure that the dimensions agree. So pi, as I mentioned, is a row vector. It looks like this. This is my pi, and this is a 1 by m matrix or vector. And basically now we have the same pi here of size 1 by m, and we have this p. This is supposed to be of the same size. This is my p matrix, and it's m by m. So this is how my teacher taught me in secondary school to multiply matrices, so that this becomes very nice. This is now pi p. All right, so you see all the matrices fit together nicely. So basically, this guy here is this guy here, as you can see. Then this guy here is this guy here. And our state transition matrix is this guy here, which is this. So they all multiply properly together, because what I get here, hopefully you can see, what I get here is this. Okay, so these two green things have the same size. Okay, every time I do matrix multiplication, I check this. Okay, unless you are very, very experienced. So all the matrices have this can multiply together. We call that they are compatible, right? So the moral of the story and the conclusion is the following: to find the stationary distribution, if it does exist, if it exists, sometimes it doesn't. Solve the left eigenvector problem. Left eigenvector eigenvalue problem, if you wish. Pi equals to pi p. Okay, so you know, okay, so i.e. find the eigenvector. Okay, hang on. Find the left eigenvector with eigenvalue 1. Okay, so this is an eigenvector eigenvalue equation. So, you know, if you do linear algebra, you learn this sort of things. Ax equals to lambda x. And this is the standard way we learn it. Okay, so when we talk about eigenvector, or when MATLAB talks about eigenvectors, they always talk about this. But because of the way we arrange a state transition matrix, we have to solve, and because of the way state transition matrices are arranged in the literature, we have to talk about left eigenvectors in this class. Okay, Now you may wonder, right? Is there such a thing as left eigenvalue? Why didn't I put left here? Because there's no such thing, right? If you look at eigenvector, eigenvalue problems, right, the set of so-called right eigenvalues is the same as the set of left eigenvalues. But the set of left eigenvectors is not the same as the set of right eigenvectors. Okay, so if you take A here, then you can find through the characteristic polynomial, you can find all these lambdas, right? And then you can plug it in again to find the x's. So those are right eigenvectors. All right. But if you want to solve for the left eigenvectors, you have to do this sort of thing. All right. So you have to find x such that when you multiply on the left, you have this. Okay. So let me arrange this properly. Lambda x. So the x's here in this particular equation are left eigenvectors. Right. Just to remind you, but I already asked you to read up about eigenvectors and eigenvalues. All right. So most of the time, you do try to find right eigenvectors. So suppose you have a software to find right eigenvectors, say MATLAB. So how do you find the left eigenvectors? Yeah, you plug the transpose into the function, right? So we just have to do EIGA transpose like that. Okay. Yeah, then we can get the left eigenvectors. That's what I will do later to show you. Okay. All right, so I have not defined the notion of stationary distribution, but I've already used the terminology here. So I have to define it properly. Definition. Okay, a steady state vector or steady state probability vector or steady state distribution or stationary distribution, they all mean the same thing for an M-state Markov chain with transition probabilities encoded in the matrix P is a row vector pi. So I will make myself explicit. 1 times n is a row vector that satisfies the left eigenvector equation. And suppose I tell you to solve this equation here. I tell you to solve this particular equation here. Can you solve it? I want a solution to this. Can you give it to me? Is there a unique solution to this? Pi equals to pi p. Okay, so you give me a solution. I will multiply that by 17. And then it's still a solution, right? So there is a scale indeterminacy here. Because you look at this, if I multiply pi by 17, then both sides, if the original pi was a good steady state vector, according to this definition, then my 17 pi is also a steady state vector. So there's some scale indeterminacy. All right, so we know that, however, that we must end up at some state somewhere. So we need to have this, okay? We need to have the normalization condition and pi I bigger than or equal to 0 for all I in M. Okay, so this if you haven't seen this before, this is my set 1 to M, okay? Shorthand. So there's a steady state vector for an M-state Markov chain. Okay, so let us gain some intuition about this, right? Before we do any more calculation and before I show you some simulations. So what happens if pi is the initial PMF of the chain at time 0? Okay, so what do I mean? Say, I mean exactly that pi I is the probability that x0 is equal to I in M. Okay, my M is my state space. So suppose I throw a rat into the Markov chain and the rat ends up in state 1 with probability pi 1. Okay, then the rat moves around the Markov chain, right? What is the chance that it will be in state 1 after a long time? Or after the next time, say time 2. So the answer to this question is not so difficult, and it's a matter of algebra. Okay, the claim is that this PMF is maintained forever. Is maintained forever. More precisely, I don't even know what this means mathematically, but the probability that xn is equal to I is equal to pi I for all I and for all n. Okay, so that's what we will prove now. So it suffices, I guess, to prove that x1 equals to j is equal to pi j. Then you just iterate this whole argument, right? Okay, so this is nothing but sum over all possible values of x0, like this, right? And probability of x1 equals to j condition on x0 equals to I. All right. So this is nothing but sum over I. Now we started off with pi I, right? Because here I'm using the fact that I started off with the initial probability at state I with probability pi I. All right. So I initialize the chain at the steady state distribution. Okay. Now this is nothing but Pij. Okay. So this is equal to pi j. And why is this so? This is nothing but adhering to this steady state equation here. Let me use this color here. This equality, this equality here comes from the fact that this is maintained. All right. Why is this so? This is because you can write this as pi j equals to sum of p I j pi I. This is just writing out the I column of this particular equation. Here I'm writing out the j column of this particular equation. Just writing out in full. And here what I'm doing is I'm just copying this. All right. From here, this is writing out the j column of this equation here more explicitly. And here we are just looking at this. Okay. So what this is saying is that the probability that I'm in state j at time 1 is exactly pi j. Okay, so this is proved for x1. Now there's another way of looking at it. We have pi equals to pi p. Okay, I think Gallager's book does it as p like this. Very funny. Okay, now we started off the chain according to this particular distribution. Okay, and this is the distribution at time, the distribution of where I am at time 1. That is after one multiplication of the state transition matrix P, right? But here, this implies that if we multiply on both sides, pi p squared. Okay, what do we get? This is nothing but pi. This is implied pi equals to pi p squared. Why? Because again, we are using the fact that this guy here is equal to this, right? Because we are at steady state. So what does the last equation say? That at time 2, the chance that I'm in state j is still pi j, right? This is the probability. This is the probability I'm in the various states at time 2. If I start at pi, so I'm still going to end up at state j with probability pi j. Okay, and of course you can imagine with your great imagination that this is going to be maintained throughout, right? Pi p n. Okay, I think the book does it like this, pn, but I'm not going to change the top. Okay, and this holds true for all n. Okay, so this is maintained throughout. So one more remark is the following. Note that if Pn converges to the rank 1 matrix, which I'll write like this. So this is the pi, row vector pi, dot, 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 row vector pi. Then pi clearly satisfies pi equals to pi p. Okay, because you can just substitute this into here. Oh, shucks. I clicked the wrong thing. Okay, then pi clearly satisfies this. So it means that each row here is a steady state vector, and there's only one steady state vector here. Okay. However, if pi equals to pi p, this does not necessarily mean that p to the power n converges to the rank 1 matrix, converges to this guy here. It does not necessarily mean, okay? And we'll see some examples of this. So we want to ask some questions, all right? We want to ask some questions, which I will list down before I do a small demo. There are 3 questions they're going to ask. Number 1, when does the left eigenvector eigenvalue problem have a probability vector solution? So a probability vector solution is one in which all the entries are non-negative and they add up to 1. Okay, the add up to 1 is obvious. All right, you can just rescale. But the non-negativity is another issue. However, the answer is always. You can find this, okay, if the P is a row stochastic matrix, which it is in Markov chains. So when is pi satisfying pi equals to pi p unique? Okay, and the answer is if and only if P is the transition matrix of a unichain. Of course, I have not defined the notion of unichain, so I'm jumping ahead of myself. But I will of course define it. Okay, so this is not enough because, as I already said, if pi satisfying this equation is unique, we may not have that Pn converges to the rank 1 matrix pi like this. We may not have this situation. So we want one more situation. We want one more question, which is when does each row of Pn converge to the same vector, satisfying the steady state equations pi equals to pi p. So the answer here is ergodic unichain. So the word unichain, uni means one, right? Uniform. Everyone wears the same shirt. Unichain. That means one something. Okay. So let me define these 2 notions, and then let me do a small little demo. So a unichain is a finite state Markov chain that contains a single recurrent class plus possibly some transient states. The key word here is single recurrent class. Now, you could have situations where you have multiple recurrence classes. Later, I'll draw a picture. Okay. So definition. How about ergodic unichain? An ergodic unichain is of course, it must be a unichain, otherwise it's a very bad name. All right. It's a unichain in which the recurrent class is ergodic. Okay. So uni means one, and it corresponds to single. Now in the homework, in a slightly advanced version of the homework, all right, which is optional, you will generalize this notion of unichain to M chain, if you would. M is not good. L chain, all right, in which you have L recurrent classes. Then you can play some games also. But in this whole class, we will only work with unit chains. And in particular, we will be interested in ergodic unit chains. Okay, so now let me show you some stuff here to illustrate each one of these points. Unfortunately, I don't have many boards here. Maybe I could have written that, but remember this, okay? Or at least you have some notes here. Okay, so now this is the first time I'm doing this. This had better work. Okay, so first and foremost, what is my Markov chain here? Okay, I will keep my Markov chain here. This is the Markov chain we looked at last time. 1, 2, 3, 6, and 4 and 5. So this goes here with probability half-half, and this 1 here. Okay, later I'm going to change some things. Okay, this is the first time I'm doing this. I'm a bit ambitious. Okay, and this, and this, and here, and there. Now, whenever there are 2 arrows going outwards, the probabilities are equal. And whenever there is 1 arrow going outwards, of course, the probability is 1. Whenever there are 3 arrows going outwards, the probability is 1/3. So I will not write down the probabilities, okay? Otherwise, it's too cumbersome. So this is what chain? Unit chain? Wait, what chain? It's not unit chain. Why is it not unit chain? Because there are how many recurrence classes? 2. Very good. So here we have 1 recurrence class, 2, 3 is 1 recurrence class, and 5 is another recurrence class. So this is not unit chain. Okay, so the state transition matrix is here. Okay, so what do I want to exhibit? What do we want to exhibit here? All right, so I want to show you something. So this is pi not unit chain 1. So that's one of my hypothesized pi's. Okay, so okay, it adds up to 1 first. It's a row vector that adds up to 1. So what do I want to show you? I want to show you that pi not unit chain 1. So that's a particular pi vector. Okay, multiplied by p not unit chain is equal to pi not unit chain 1. That means that the steady, if this whole thing, when I run it, is 0, that means that the steady state equation is satisfied. Okay, so this pi not unit chain 1 is indeed satisfying the steady state equation, which is, let me remind you, pi p equals to pi, right? So I satisfy this equation here. So now this pi not unit chain is this 0.00.5, 0.000, right? So I can propose one more for you, pi not unit chain 2. Okay, this adds up to 1 also, right? But if you look at this, I do the same thing. So hopefully this is 0. So again, this equation will be satisfied, this equation here. You see, now we have 2 probability vectors that are very different, and it satisfies the relation pi p equal to pi, right? So you see, I mean, this is not a unit chain, and so we don't have unique, right? We don't have a unique probability vector solution. Now, how can I make this a unit chain? Okay, so I make this unit chain here. So what did I modify? 5. Now, if you look at 5, I go to a 5 to 1. Okay, so what I modified is the following. So if you look at the 5th row here, okay, if you look at the 5th row, I go 5, half, and 5, oops, goes to 1 here, half. I modified this a little. So now I modified the chain a little bit, right? Now, do I have a unit chain? This is the unit chain, that's why I call it P unit chain. All right. So how do I show that there is a single probability vector solution that satisfies the relation pi p equals to pi? There's only one. Any suggestions? So let's do this. Well, what do I'm doing here? VD equals to I P. No, I want to do unit chain. Okay. What do I see here? What I see if I run it? You see that this eigenvalue, the vector of eigenvalues, right? This is D, the vector of eigenvalues. There's only one. So that means that here, for the eigenvalue that is 1, the eigenvector, this guy here is unique. You have no repeated eigenvalues. Oh, I need to do this prime here for transpose. Okay. So this means that this particular transition matrix here has a unique pi that satisfies pi p equals to pi. All right, because you have this single one here. So what if we want to do something funny, which is not unit chain here? Oh, you see the D part. So you'll see that, oh, if you squint carefully, there's 1 and 1 here. So that's why the number of ones here actually captures the number of recurrence classes that you have in the original chain, where 5, here 5 only, 5, 1 here. There's a self loop here, and there's no artificially created half here. Okay, understand? So this answers 2 of my questions already, at least through this example. But is this whole thing here an ergodic unit chain? What's ergodic unit chain? Ergodic unit chain means that the recurrence class is ergodic. Ergodic means recurrent and aperiodic. So my recurrent class here is 1, 1. Okay, so the period there is 2. So you're very fast with this, right? You need to think very fast. So the period here in this recurrence class is 2, right? So what do I have here? Okay, now let's try, what do I want? Unit chain. All right, let me look at this. Okay, let's do power of 10 to see whether it goes to a rank 1 matrix. No, maybe if you are not convinced that 10 is not enough, okay, 10 may not be enough, it's 100. Is this rank 1? No, not rank 1. You see that this is rank 2. All right. And in particular, all the rows are not the same. The rows are not the same, right? So the rows are not the same. So the reason is because this is not a unit chain. This is not a unit chain because this part here has some period 2. It's not ergodic. Yeah, here got period 2. All right. So now I'm going to artificially change something as well. P what? What do I call it? Ergodic unit chain. Okay, what did I do here? So I made state 2. Okay. State 2, I modified state 2 so that it goes to state 3 with probability 0.1. And it goes to state 6 with probability 0.9. So I deliberately made this. Okay. So that I deliberately changed this row here. Okay, so compare to what is it? Unit chain. Yeah, you see, I changed the second row. So now we are focusing on this ergodic unit chain, okay? Focus on the ergodic unit chain. So one thing to check is the eigenvalue of ergodic unit chain. All right, first and foremost, you see that, okay, there's some imprecision here because of this stupid computer, but there's only one eigenvalue. There's only one eigenvalue that is 1, okay? So that means that we have a single pi that satisfies pi p equals to pi. Single, okay? Because the eigenvalue here is 1 eigenvalue. Next thing here is we are interested in taking the power here. Okay, hopefully it's going to be rank 1. Okay, 10 is not enough. 10 is still not very clean here. But as you see, if I increase this to 100, all the rows are the same. All right, if you don't believe me, then you can do rank here. And you see the rank one. So you see, by successively modifying this Markov chain, we can get to different sorts of behaviors. And this is the sort of behavior that we will be analyzing in this lecture and the next lecture. Okay? Cool, right? Okay. So this is rank one, as you can see. If I raise it to 100, actually no need 100, I think 40 is enough. Just now I tried. Oh, not enough. Oh, maybe you need a little bit more. Okay? But still not enough. 100 is a sweet spot. Okay, but in any case, you really need to be long enough. And we will see that this rank in MATLAB is also not very good. It's very sensitive, right, to small little changes. So that's not very good. Okay, so I illustrated all the behavior. Unfortunately, I cannot have many screens on at the same time. Okay, so now let me talk a little bit more about this thing here. Okay, so just now we saw an ergodic unit chain after suitable modification of the Markov chain we talked about last time. Okay, so the point is the following. The point I want to make, and I will show another demo later. So for some Markov chains, and in particular ergodic unit chains, okay, we have the following behavior. Oh, we have one friend joining us. We have the following behavior. Okay, so here what I'm plotting is n, and this is pi j. So that is the long-term behavior. There's a long-term behavior. There's a long-term probability of us landing in state j. Okay, and this is, as time goes on, this is the max over all possible values of I, Pijn, and this is the mean over all possible values of I, Pijn. So we are going to prove this. We are going to prove this behavior for ergodic unit chains very shortly. Okay, so our objective is to study the difference between the largest and smallest elements. And from finite state Markov chains, this is well defined, of each column of Pn as n tends to infinity. And see how this difference, and the difference is basically this gap here. Let's see how this difference evolves with n. If this difference converges to 0, the max and the min are going to kiss each other as n becomes large. And then they are going to be independent of the I. Going to be independent of the I because the max and the min coincide. And so the matrix goes to a rank 1 matrix where all the rows are equal to pi. So that is our objective. Okay, that is our objective for the rest of the lecture today. Now to show you that it is not a fluke, all right, let me show you something else. Okay, so now I have this ergodic unit chain here. For this, I need to write this loop here. Sorry, this is not very professionally done. And so here, I only use 30 iterations, okay, and initialization. So this is the ergodic unit chain that I created just now. And I take successive powers. And now I'm just looking j equals to 1. So here, j equals to 1. You can do this for all j if you like, okay? And this is the max, this is the min, all right? And this plotting. So when we run this, we see that, okay, the top is the maximum, the bottom is the minimum. It converges to this point here. Okay, and what is this point here? This is 0.2 something, I don't know. But if you take ergodic unit chain just now and you take power 100, it's 0.2118. It converges to this. So that's the mean and that's the max. That's the mean. The mean is the red line. The max is the blue line. Yeah, see? So you can do this for all possible. You can change this to j equals to 2. How would you change to 4? Okay, let's see what happens. Everything goes towards 0. Why? Because in my chain, oh, I lost my chain. But my chain 4 was the only transient state. The last modified chain. All right, that I don't have it anymore. But no matter what you change this number to, you will see that this blue line and red line will converge to the corresponding column of this power matrix. Okay, I illustrated this for the first one. You can do it for the others. Okay. All right. So now there are a few things we want to prove. Just a couple of things, and then we will call it a day. Because I guess after the quiz, your mind is also a little bit frazzled. Okay, so I want to prove a few things. All right, so lemma. The first lemma we want to prove is the following: that the max never increases and the mean never decreases. For every state j, and for every n bigger than or equal to 1, the maximum over I of Pij n plus 1 is less than equal to max over L of Pljn. And of course, we have the same expression. Mean over I of Pijn plus 1 is bigger than mean over L of Pljn. Okay, let me make this nice. Pljn. With course, I will only prove the first statement. You can prove the next statement. Okay. So what does this say here? All right. What does this say? Look at the picture. This says here that as I increase the iteration count, okay, the max cannot increase. So you cannot see this jumping up like that. Can never. But this does not say that we have strict decrease. This does not say that we have strict decrease like in this picture. For that, we need a little bit more. We need ergodic unit chain. All right. But what this says is we cannot increase. This warm up, a warm up for the case where this decreases. Okay. So another thing for you to note is that the arc max here and the arc max here may be different. That's why we need max max. The arc max may be different. The point at which we attain the max may be different. No one says that they are the same. Okay. But here we just say that we have this sort, we can potentially have this sort of going down behavior. We cannot have going up behavior here. Okay. So the proof of this is not so difficult. It's a matter of applying the Chapman-Kolmogorov equation properly. Okay. So we start with the left-hand side. Fix any I. Fix any I. I state I in state space and n in n. Okay. Then let's consider Pij n plus 1. Okay. This is equal to sum, or actually we should fix, we should fix any ij in S. And this is by the Chapman-Kolmogorov equation, Pik Pkjn. All right, so this is splitting. We have done this before many times. Okay, so now we are going to be very conservative and we are going to sum over all possible values of k, Pik. We are going to keep this here, Pik, and max over L Pljn. Okay, so this guy here, a lighter color, this guy here serves as an upper bound to this guy here. Now, this is to make sure that this is independent of k now. Okay, so I take away the dependence on k, I just max. Note that j is always fixed, so I'm not touching the j. I'm just maximizing over the k here. I don't like the k here. This is being very conservative. But what do we notice? Now, this guy here in the orange does not depend on k anymore, so it can move outside here. Right? That's what we will do. This is equal to, I move it outside, max over L, Pljn, sum over k, Pik, and this is equal to, I need an answer from the audience. This guy here is equal to how much? 1. Perfect. So what we have is just this guy here. Okay, and Notice that now this holds true for every I, for every I. So here, this I is a free parameter. So maximizing over all possible values of I, we get the desired result. Okay. So this proves the max version. All right. So this sort of simple thing I will ask. All right. Because this tests your ability to write out the Markov property here. All right. So this sort of simple thing, yes, I will definitely ask in the exam. This is n step from I to j. You decompose it into one step from I to k and n step from k to j. Now, I don't like this intermediate k, so I'll max over all possible values of L, but you'll see that in the next proof, the next statement, this is very conservative. We can do better. Okay, you can bring this outside because it has nothing to do with k, and then this guy here is equal to 1, as many people here told me. Okay, because at I, you need to go somewhere, and I'm summing over all possible values of states k, so this must be equal to 1, and so now we have that this I is a free parameter that allows us to maximize over. Okay, so this is a simple result. So just a small remark. The max over all elements of a fixed column J, okay, is non-increasing. But non-increasing is not good enough for us. We want strict decreasing, okay? So now as a prelude to what we'll do next time, as a precursor to what we'll do next time, okay, we will consider a simple scenario. Consider the scenario in which the matrix P is greater than 0. What this means is that Pij bigger than 0 for all ij in the state space. Now, this is the lucky scenario. There's enough mixing everywhere. So notice that in my MATLAB simulations there, right, there are many zeros. So this is a very bad assumption. Here, this says that I can go from every state to every state in one step, right? Because I have this P matrix that is all positive everywhere. But this is good enough for most purposes. Why? This is good enough for, in particular, ergodic unit chains. Why? Because I don't know whether you remember or not just now at the very beginning, and maybe after your quiz, you are very frazzled. At the very beginning of my lecture here, I already said that if you have an ergodic unit chain and I raise it to the m power for m sufficiently large, this is all positive. For m bigger than m minus 1 squared plus 1. So for ergodic unit chain, if I wait long enough, every element in the matrix is positive. Okay, so now what I'm assuming is that, okay, I'm already there. I've already waited sufficiently long so that I have this condition. Now let's play with this condition first. Then later on in the next lemma, we will bootstrap this in order for us to attain this, to make use of this lemma here. Okay. So what I'm saying is that for ergodic unit chains, we have this, for ergodic Markov chains, we have this behavior here. For m sufficiently large, every element is positive. Now let us just assume that we are already there. All right, m is already sufficiently large so that all the elements of P are positive. Then let's work with that first as a simple case. Because if we cannot walk, we should not fly. Okay. So let's consider this scenario. Now, the next lemma I'm going to prove is exactly this picture here, that the maximum actually decreases by a fixed step size each time, by a fixed multiplicative constant each time. Okay, so more precisely, lemma. Now define alpha as min ij Pij bigger than 0. Why is it bigger than 0? Because I said so, right? Because we consider the scenario, make this assumption here. The assumption for the next lemma is this. Okay. So if all the elements are positive, clearly the minimum is positive. And so I'm going to give that a name. I'm going to call it alpha. Okay. Then for all states j and n bigger than or equal to 1, I have the following. Max I Pij n plus 1 minus min I Pij n plus 1 less than equal 1 minus 2 alpha. Okay, the exact same thing here where I change n plus 1 to n. Okay, so what does this say? All right, what does this say? This says that we have max over L of, why do I have L here? Maybe I is good enough. Pijn minus min of I. Pijn is less than 1 minus, by induction if you wish, power n. And that means that limits as n tends to infinity of max over I, okay, we don't need to be so fancy, Pijn equals to the, this is by the so-called squeeze theorem if you wish, min over I, Pijn is greater than alpha greater than 0. But the point is that the limit of the maximum is the same as the limit of the minimum. Okay, so what this is saying is that, all right, in particular, this statement is important. Alpha is something that is positive. Can alpha be bigger than half? In which case, this guy here is oscillating. Can alpha be bigger than half? Now, alpha is bigger than 0, okay? Can alpha be bigger than half? Say 75%, 0.75. It cannot, all right? Because this is the minimum, it's also upper bounded by half. Because there must be a complementary probability that you add on to. So this guy here is at most half. Okay? Because if it were greater than half, right, then probabilities would sum to bigger than 1. Now, if this were big, if alpha is bigger than half, this would oscillate, which makes no sense. So maximum is always bigger than minimum. Maximum is at least as big as the minimum. This guy here is contractive. So this guy here, the factor here is less than 1. I mean less than 1 power n becomes smaller and smaller very, very fast. Like 0.8 to the power of n. Drops exponentially fast. Right? So what it's saying is that the max and the min are getting closer and closer. They get squeezed together. They get squeezed by a term that is exponentially decaying. So in this picture here, if I look at this sequence of differences here, the sequence of differences here gets squeezed by a quantity that is exponentially decaying, because this term here is exponentially decaying. Okay? The details of the proof are not very difficult, but the meaning here is more important. Okay. So this dilemma that we're going to prove in a short moment, we will take this 10 minutes to prove it. But the good student will ask a question here. What question will a good student ask? At least I will ask the question here, because I mean, you know, my job is an information theorist. Information theorist means we prove theorems to say that you cannot do better than something. That's my day job. I prove I'm information theorist. So information theorists will ask, hey, okay, you have such a statement here. All right. This is the sort of thing that you should take away from this class. Huh? After you finish with the exam, when you look at such a statement, you should immediately ask a question. Is this the best possible? So say this is 0.8 to the power n. Is this the best possible you can do? Can you do better? Can you get 0.3 to the power n? Because that decays much faster. All right. So we have this, say this is 1 minus alpha n, 1 minus 2 alpha power n. Say this is 0.8 power n. Now, if I give you a Markov chain, now I'm going to use this technique to prove something. But the Markov chain actually converges much, much faster, like this. That means this proof technique is not very good, right? It's okay because you get a bound, but you do much, much better. That means your proof technique is not very good, and you should improve on this analysis. So The point I want to make here is that next lecture, we're going to improve on this. This is a very naive analysis that makes use of the simple property of the Markov chain, that its elements are positive. All right. But next time, we will look at exact speed of convergence, and we'll be able to nail down how fast this goes down to zero. So after you take this class, it doesn't really matter whether you remember the techniques or not, but you should be sensitive to these sort of questions. You should be sensitive to whether this is the best possible or not. All right, like me. Okay, so let's prove this. So this is just a I would say warm up for the next time. Okay. So before we prove this, maybe I can write a remark. All right. This implies that elements of Pijn for column J of P power n achieve equality over I as n tends to infinity. Notice in the previous result here, right? Now, you have this sort of result, but this does not preclude the situation where this is always equality. You don't make any improvement. You don't make any improvement. You don't become worse, but you don't become better. All right? But here we are saying that, okay, you are going to become better by this factor, 1 minus 2 alpha. Okay, and 1 minus 2 alpha is strictly less than 1. Okay? So, this is the last proof. I guess it's the last proof I'm going to do. Okay? Today. All right. So, proof. This proof is a matter of careful bookkeeping. Careful bookkeeping means you are very careful. You don't throw away things. Here, what did we do? Here, oh, this one, upper bounded by max. Now we are going to be more careful. All right. So let L min be equal to up fixed J. Fixed J in the state space. Let L min be the up min over L in the state space of PLJN. So we note that a very important property is that sum over K not equal to L min of PIK equals to 1 minus PIL min. Okay, we fix I and J in S as usual, and fix N in N. Okay, so why is this true? We need to make use of this small little result, because if I move this over here, I get 1. I need to go somewhere from I. So I just write it in this way because later we're going to use it. Okay, this proof looks a bit magical. Okay, but all these proofs start from the Chapman-Kolmogorov equation, which is Pij n plus 1. We are going to decompose this in the usual way. Equals to sum over all possible values of K, Pik, Pkj power n. Okay, just now what do we do? Oh, we look at this one and we max it over K to get L. All right, so we are not going to do such a loose thing this time. I'm going to split this into K naught in L min, Pik, Pkjn plus Pil min. This is a bracket here. Pil min and Pl min. I'm going to write it like this. Okay. Notice that this is exactly P of L min J n by this definition. Okay. By this definition, we have that this is true. So I'm just writing it in a slightly different way. So this is a careful decomposition. All right. So now what we will do? We will do the following. Sum K naught in L min. We are now going to be conservative. All right. We are going to max over L of PLJN. This is what we did previously. This is exactly what we did previously. Okay. And this one we will just copy down. All right. So this is a little bit technical. Oh, this is just a little bit technical, but hopefully you appreciate the use of the Chapman-Kolmogorov equation. Okay, we are just copying this down, so I don't have to write. Okay, so what do we do here? Basically, we just maximize this over all possible values of J. No harm. Okay? And we call it max over L. Maximize over all possible values of K. Basically, we call that max L. All right? So the next thing we're going to do is that we're going to rearrange. Okay? Now, here in my previous notes, I did this very quickly. Max over L, PLJN. And we have this term, right? This term that I just bracketed. But this term that I bracketed is exactly equal to this guy here that I highlighted before. Okay? So I said note that. When I say note that, I really mean note that. See this? Okay? So now I'm going to copy this and I'm going to put it here. This is exact equality. Okay? This. Now this part here is a little bit painful, but we have to get through this to show you that the convergence. I'm keeping it here. Okay, so now what do we have? We are going to have max L PLJN minus PIL min into max L PLJN minus min L PLJN. This is a matter of algebra. I will not belabor the point. This is a matter of algebra. Okay. Basically, you take this multiplied by 1, you get this guy here, and then you take this as a common factor out, and then you have max and min, you combine this here. Algebra. But now, what are we going to use? Okay, now this guy here is non-negative. Right? Max can only be bigger than min. Need not be bigger, but it's non-negative. So what we can do is we can control this by, Now, here's where I introduce my alpha. Ah, man. Here's where I introduce my alpha. I copy this exact thing here. But now, because this is non-negative, and I know that all my elements are bigger than alpha, or bigger than or equal than alpha, this is alpha here. I can do the following. Okay? You see? Because this guy here is bigger than or equal to alpha. So I can replace PIL min by alpha. Okay? There's no harm. Now, so we have this sequence of inequalities. Now, I'm not going to do the converse, the reverse inequality. I just say similarly. Okay? Pijn plus 1 is bigger than min over L, PLJN plus alpha. Same thing. Okay? Same thing here. So we have these two equations here. So let me just put Pijn plus 1 here. All right. So now, what can we see here? Ah, we can string these two things together. These two are the same. We are going to string these two together. And what we see here is that we will have max over I, Pijn plus 1, Pijn plus 1, minus min over I, Pijn plus 1, less than 1 minus 2 alpha. The 2 alpha comes from this alpha and alpha. And we have the same thing, which is this guy here. So we have this contractive behavior. We have contraction. Contraction means this goes down, right? Geometrically fast. Okay, so this is equation 1, this is equation 2, and here equation 1 union equation 2 use this guy here. So this is exactly what we wanted to prove. Okay, this is exactly what we wanted to prove, because now we have this contractive behavior. This is a sequence. Say this is an plus 1, this guy here, 1 minus 2 alpha, an. So the sequence here becomes smaller and smaller, each one by a geometric factor that is constant. Okay, so this proves the result. Okay. So this is a matter of 1-2 rearrangement. Okay. So what we have proved here, all right, in this particular lemma can be summarized a little bit better in this theorem here. Okay, let P be the transition matrix of an ergodic Markov chain. I think we have not proved this yet. Let me just keep it simple. Let P be the transition matrix, okay, such that P bigger than 0. That means that all the elements are positive, all right? Then there exists a unique steady state vector pi, which satisfies pi bigger than 0. This means that all the elements of the vector are positive. Okay, in which pi is bigger than 0, and pi is pi p. Well, that's the meaning of steady state vector. Sum of pi j equals to 1. And furthermore, the convergence is ergodic. Is geometric in N. Okay, so the convergence decays. Basically, the max and the min here. The difference here, this is called the gap, if you wish. The gap at time n plus 1 is less than or equal to some factor, the gap at time n. Okay, so we have this geometric convergence. And furthermore, we have this scenario here, the pi is positive at convergence. So this comes to the fact that we can now call this pi j, all right? And pi j is bigger than alpha, bigger than 0 here. This comes from this fact. Okay? If P is positive everywhere, then we will have such an alpha and the limit will be positive everywhere. Okay? So let me go through this argument one more time because I think it illustrates a few points here. Okay? So what is the statement? Now I assume that I have a matrix that is positive everywhere. Okay, then what happens here is the minimum value is of course positive. Then for all states j and all n plus 1, this is my claim. And this claim here substantiates this picture here. Okay, that means the gap is always decreasing, strictly decreasing by a fixed amount each time, not by a vanishing amount. All right. Okay. How do I get rid of this? Man, how do I get rid of this thing? Okay, then we have this scenario here, geometric decay. Okay, so what is the proof like? Fix all these constants here, 2 states in a state space, and n in n. Let L min be the arcmin of P, L, J, N. Right, and note that we have this conservation of probability because this, if you move over here, you will add up to 1. So now this is the Chapman-Kolmogorov equation, but we do this very carefully. Okay, we split into the L min and not the L min. This is not the L min and this is the L min. Now, then we look at this orange part. It can be maxed over. All right, this is the minimum. But now this guy in green here, can be replaced by this guy in green here. Right, and now this is a matter of rearrangement to take out the max here and to replace everything else here. But now we make use of the fact that alpha is a lower bound on this guy, or the lower bound on every probability. So we have this. Now, in a completely analogous and similar manner, we have the lower bound here. So combining the upper and the lower bounds, we get this. And so we have this gap contraction. The gap contracts, becomes smaller each time by a fixed amount. And thus we have this theorem here. P is a transition matrix that is positive everywhere. Then there is a unique steady state vector which is positive everywhere, and it satisfies this relationship. And the convergence is geometric in N. Okay. Now, so the following theorem is also true. Okay, and it just requires a one-line proof. Okay, which I will do perhaps next time. So if P is ergodic, right, then the same is true. The same, what is the meaning of same? The same is true means that there exists a unique steady-state vector, okay, for which we have the normalization and we have this, and the convergence is also geometric in it. So that I don't have to copy out. The same is all the green stuff. Now, note that this guy here is certainly ergodic. All right, but if you're ergodic, you need not be this. All right, so if you're ergodic, it just means that the recurrence class is aperiodic. There's no period in there. Okay, so why is this true? Okay, so if P is ergodic, all right, then it is true that pH, I think I call it PM last time, so let's call it PM, is bigger than 0 for all H bigger than M. I'm following my notes. M bigger than M minus 1 squared plus 1. So if you take M to be sufficiently large, then you have a positive matrix, not non-negative, but positive matrix. Okay, so we can then just apply the previous result. Roughly speaking, apply the previous result. The previous result is this theorem star, okay, to pH or PM. Okay, because the PM is positive. So that's the main idea. I think the book does it much more carefully, but it's believable, right? I just have to do the case in which everything is positive. It's believable. Because now if we have this ergodic situation, then we are able to form this matrix here, and this matrix is positive everywhere. And so we are good. We can apply the previous result. Okay, so notice here that we have this positivity situation. Okay, the pi j that we learned, the pi j, which is steady state, is positive everywhere. Now, this comes from the fact that the matrix is all positive. Okay, all the elements in the matrix were positive. I think I did an example just now to show you that in fact some things can break if the matrix is not positive. So now let's look at P ergodic unichain. It's like this. See, there are many zeros. Okay, see, okay, there are many zeros here. So now this is an ergodic unichain. Very nice already. All right. Now it's also true that if I raise this to power 100, maybe what if I raise to power 100? Okay, all zero. Really rank 1. That 1000 power. You see that all the rows are the same. But if you call this guy here, pi j, if you call this guy here pi j, each row here pi j, you see that we don't have the situation that pi j is bigger than 0 for all j, because in particular this guy here is 0. What went wrong? Well, what went wrong was that P ergodic unichain has a lot of zeros. All right. Now, if you can create some matrix here that does not have zeros, then it is okay. If you can create a matrix here that is dense, no zeros at all, then what we have proved is that it will go to this sort of situation. It will go to this sort of rank 1 matrix where the rows here are all positive. All right. So this ergodic unichain here has a slight problem that does not satisfy our theorem, the last theorem that I proved. Okay. So today what we showed is the following. So share. So now, just to conclude, all right, we have proved this thing here. Just to conclude, if we define the vector, just to make this formal, I think I've already done this, pi 1 up to pi m greater than 0 by pi j equals to limit as n goes to infinity of max over L PLJ n equals to limit n going to infinity of minimum L PLJ n greater than 0. Okay, what we have here is that Pn will converge to the matrix, to the rank 1 matrix with all rows governed by pi. Okay, as n goes to infinity. And this holds for ergodic situation, ergodic Markov chain. Okay, unit chain. Okay, so next time I will show uniqueness, and next time we will talk about rates of convergence. We will talk about how fast actually this goes to the limiting distribution. That's what we'll do next time. Because as I always mention, okay, what you want to get out of this is that this analysis here gives you this bound here. Who says that this bound is very good? No one says so. Next time we will improve on this because this is not optimal. If we want the best bound, we have to actually look at the spectral properties of P. We have to look at the spectral properties, that's the eigenvalues, eigenvectors of P. Okay? And this will govern how fast it reaches equilibrium for the steady state distribution. Now, you might think that this is very abstract and very, I don't know, very theoretical. But in fact, this sort of techniques, spectral techniques that we'll talk about next time, they are used extensively in what I do these days, which is graph clustering in general, because we make use of spectral methods. So we have to understand the spectral properties of matrices, the eigenvalues, eigenvectors. Now, if you go a little bit further and you talk about tensors, which are bigger matrices, higher order arrays, all right? Then we can also talk about their spectral properties, and their spectral properties govern how fast they converge to a certain limiting distribution. All right, so these are really important in applications, and this is just the tip of the iceberg. Next time we'll talk more about this. All right, thank you. Hopefully you found the quiz okay. Thank you. See you next time. Bye-bye. Yeah.
About the last information.
Yeah.
I don't get why.
Hang on, let me stop Zoom first. Let's stop Zoom. Don't just